All right, so like I said, we're starting chapter 7. We're going to focus on frequency response of dynamic systems and then Bode diagrams. We previously dealt with frequency response in chapters 2 and 3. There we derived what was known as the frequency response functions. We did that from a vibrations perspective. Here we're going to use Laplace transforms as a way to compute frequency response through the transfer function for a system. Then we're going to encounter a common tool for visually depicting transfer functions or frequency response functions, which is known as the Bode diagram. All right, we're going to first take a look at the relationship between frequency response functions, which we studied earlier in the semester, in the beginning of the semester really, and then transfer functions, which we studied more recently. We're going to start by considering just a damped harmonic oscillator with some external forcing f of t shown here. F of t is just some generic force. And the equation of motion for this system is going to be mx double dot plus bx dot plus kx, and that's then equal to the external force f of t. We're going to give this 0 initial conditions. So x of 0 is equal to x dot of 0. Both of those equal to 0. And then this will allow us to compute the transfer function using Laplace transforms. So in chapter 2 of our notes, we found that the frequency response function for harmonic forcing of the system is the function h of omega is equal to, for this system, the fraction with 1 in the numerator, and then in the denominator we're going to have k minus m times omega squared, that's our real part, plus j times b omega, and that's the complex part. And you can expand this into terms using the natural frequencies and damping ratio, and you'll get 1 over m in the numerator, and then in the denominator we'll get omega n squared minus omega squared plus 2j times zeta n omega n times omega, where zeta n and omega n are the damping ratio and natural frequency of this oscillator. All right, so we're now going to use Laplace transforms to relate our transfer function to the frequency response function that we have up here. We're going to proceed by taking a Laplace transform of equation 1, both sides. We're going to get that Laplace transform of mx double dot plus the Laplace transform of bx dot plus the Laplace transform of kx is equal to the Laplace transform of f of t, which we can then find that this will be equal to the quantity ms squared plus bs plus k, all of that multiplied by big X of s is equal to big F of s. All right, we're now going to compute the transfer function, which we call g of s. This is going to be equal to x of s divided by f of s. In this case, these are both scalars. X of x and f of s are both scalar functions rather than vector functions, so we can just straight up divide them. And then what we'll find is that our transfer function g of s is equal to still x of s divided by divided by f of s. That will be equal to the quantity 1 divided by ms squared plus bs plus k. From here, we're going to make the substitution that S is equal to J omega. And then we're going to get G of omega is equal to big X of omega divided by big F of omega, which is then equal to the fraction where we'll have M times J omega squared, that quantity squared, plus B times J omega plus K, 1 divided by all of that. And then what we'll end up with is that G of omega is equal to 1 divided by K minus M omega squared plus J times B omega. So thus we find that the frequency response function is equivalent to the transfer function with S equal to J omega. So if we make the substitution S equals J omega and plug that into a transfer function, we will get the corresponding frequency response function. Such that we can write here that we'll leave it a little more general, say G of J omega is equal to H of omega, which is our frequency response function, equal to 1 divided by K minus M omega squared plus J B omega equal to 1 over M divided by omega n squared minus omega squared plus 2J times zeta n times omega n times omega. All right, so typically in vibration analysis, you would typically use what's known as a Fourier transform in order to compute a frequency response function. But when we're dealing with system dynamics, we're going to use Laplace transforms to compute a transfer function, and then we'll make the substitution S equals J omega. And these are totally equivalent operations, either applying a Fourier transform to get the frequency response function or applying the Laplace transform and then making the substitution. And the reason for that is that what's known as the Fourier transform is a special case of what's known as the bilateral Laplace transform. We're going to see that in a moment. Just for your knowledge, the Fourier transform f of omega is equal to the integral from minus infinity to infinity of e to the minus j omega t times f of t dt. So this is the Fourier transform. We're computing the transform of the function f of t with respect to e to the minus j omega t. J is still our imaginary number here. And then the bilateral Laplace transform is defined as we'd write f of s is equal to the integral from minus infinity to infinity of e to the minus st times f of t dt. So this is just the Laplace transform, except instead of integrating from 0 to infinity, we're integrating from minus infinity to infinity. And what you can see here is that the Fourier transform is equivalent to this bilateral Laplace transform so long as s is equal to j omega. So in other words, the Fourier transform is a special case of this. special case of the bilateral Laplace transform. All right, just for your knowledge, you should note that the Fourier transform is very frequently used in signal analysis, by far the most used transform, and because it provides provides insight into the underlying frequency constant captured by that signal. However, the signal must be linear and stationary. Stationary means that the components that make up the signal, their frequencies do not change in time. If you have what we call a non-stationary signal, you should be using some other type of transform, such as the continuous wavelet transform, a Gabor transform, or something like that. Generally, we use the continuous wavelet transform. And this will give you a time frequency representation, so you can study how the frequencies of those components change with time. That's just a little side note. On top of it, this being a little aside section. Okay, so we're now going to use the Laplace transform to find our frequency response function, or FRF, for any dynamical system where you can do that. We're going to go through a couple of examples of how to do this, at least one example, and then we'll look at what happens when you have multiple inputs and multiple outputs, and then we'll look at another example there. So for this system here, we are given a 2-degree freedom system without any damping in it and just 2 springs there shown here. The first mass is forced with a external forcing f of t, and then we're asked to compute the FRF of this system using the transfer function approach, and we're given the equations of motion. In chapter 3, we previously computed the frequency response function for this system, or at least the amplitude of the frequency response function, by assuming a steady state solution, plugging that in, and then deriving the amplitude of that steady state solution. Here we're going to go and use Laplace transforms to find the transfer functions for this system, and then we'll go and compute the frequency response functions as well. And since there's no damping in the system, we'll find that those functions are real. All right, so to compute the transfer function, we're going to first start by assuming 0 initial conditions. So to compute the transfer function, we assume 0 initial conditions. Meaning that the initial displacements, initial velocities are both 0 for both masses at time t equals 0. Or, we'll just write it out, x1 of 0 equals x2 of 0 equals x1 dot of 0 equals x2 dot of 0, and those are all equal to 0. From here, we're going to take the Laplace transform of each side. So we'll just write taking the Laplace transform of each equation. We're going to get m1 times the Laplace transform of x1 double dot plus k1 plus k2 times the Laplace transform of x1 minus k2 times the Laplace transform of x1, of x2 in this case, equal to Laplace transform of f of t second equation, we're going to get m2 times the Laplace transform of x2 double dot plus in this case just k2 times the Laplace transform of x2 minus k2 times the Laplace transform of x1 is equal to the Laplace transform of 0. So it's going to give us the following. We're going to get m1 s2 squared plus k1 plus k2, all of that times big X sub 1 of s minus k2 times big X2 of s is equal to big F of s. Second equation gives us m2 s squared plus k2 times big X2 of s minus k2 times big X1 of s is equal to 0. From here, we're going to divide both equations. By f of s. And we're going to let g1 of s be equal to x1 of s over f of s, and g2 of s be equal to x2 of s over f of s. So we have two transfer functions for this system. All right, so this is going to give us that m1 s squared plus k1 plus k2 times g1 of s is equal or minus k2 times g2 of s is equal to 1 because we've divided by f of s. Then our second equation, we're going to have here m2 s squared plus k2 times g2 of s minus k2 times g1 of s, and that's equal to 0. We're going to take the second equation and we're going to solve for g1 of s. And we're going to find that g1 of s is equal to m2 s squared plus k2 divided by k2 is equal to g2, or multiplied by g2 of s. We're going to take this and we're going to plug it into the first equation, and then we're going to solve for G2 of S. And once we know G2 of S, we can then go and compute G1 of S, and we'll have found the transfer functions for this system. All right, so we're going to substitute in. We're going to get 1 over K2 times the quantity M1 S squared plus K1 plus K2 times M2 S squared plus K2 times G2 of S minus K2 times G2 of S, and that's equal to 1. From here, we're going to multiply by K2, and then we're going to group up terms. So we're going to get quantity M1 S squared plus K1 plus K2 times M2 S squared plus K2 minus K2 squared, all that times G2 of S is equal to K2. Yeah.
I'm realizing 2 lines up when you computed G1 of S as a function of G2 of S. Wouldn't the denominator in that fraction to the right be K1, not K2? It won't make a huge difference later on, but like that term on the right that's K2 squared should be K1, K2.
You're talking about here. So you're saying that there's an error here.
Oh, did I write that wrong? I might have written that wrong. No, wait, no. If you go up previous to that, oh no, I might have been writing K1 where I was supposed to write K2.
Yeah.
Yeah, no, I gotta go back to the previous page. Whoops.
Yeah, the coupling spring here is K2, and so in the second equation, there's no grounding spring. But don't worry, I found an error in chapter 3 because of this analysis. But I corrected that. You guys don't need to worry about that. It doesn't really change much for you. I think it's an M1 instead of an M2 in chapter 3. And in that example, we actually plotted it, but we set both masses to 1, so it didn't matter anyway. All right, so this is equal to K2. We can now solve for G2. So we get G2 of S is equal to the quantity. We're just going to get K2 by itself in the numerator. The denominator, we're going to get M1 S squared plus K1 plus K2 times M2 S squared plus K2 minus K2 squared we can substitute this in for our expression for G1, and we'll end up canceling a K2. And in our numerator, we're going to get that this is equal to M2 S squared plus K2 in the numerator. Denominator will get M1 S squared plus K1 plus K2. M2 S squared plus K2 minus K2 squared. And just as a note, if you do try to compare this analysis to what we have in chapter 3, and chapter 3, in that example, we have an M1 there, but it's wrong. Okay, we now found our transfer functions. We can let S equal to j omega, and then we'll be able to find our frequency response functions. We'll get that h1 of omega is equal to big fraction of k2 minus m2 omega squared divided by the quantity k1 plus k2 minus m1 omega squared times quantity k2 minus m2 omega squared minus k2 squared. And it's 2 of omega. It's going to be equal to still just k2 in the numerator, and then the same denominator. So k1 plus k2 minus m1 omega squared times k2 minus m2 times omega squared. All of that minus k2 squared. So up here we had our transfer functions. And down below we have the frequency response functions, or the FRFs. Okay, so we can also do this analysis using matrix forms, and we're going to show that now. So we're just going to write here, note that we can also perform this analysis. Using matrix forms. We're going to start by placing the equation of motion into matrix form. So in matrix form, we're going to get M1, 0, 0, M2. Then x1 double dot, x2 double dot, plus matrix k1 plus k2 minus k2 minus k2 k2 times x1 and x2. And that's equal to the forcing vector f of t and 0. Or in condensed form, we can just write this as mx double dot plus big Kx is equal to big F of t. All right, we're going to take the Laplace transform of this. We get Laplace transform of m times x double dot plus Laplace transform kx is equal to the Laplace transform of f of t. So will give us s squared times m plus k, and that quantity times big X of s equal to big F of s. Such that x of s is going to be equal to the inverse of s squared times m plus k, inverse of that, times f of s All right, so thus the transfer function is q of s is equal to s squared times m plus k, the inverse of that, and then the FRFs are, say, h of omega is equal to, we substitute s equals j omega, and we'll get back here k minus omega squared m, and then the inverse of that. All right, we're going to note that because there is no damping in the system, this FRF is going to go to infinity whenever omega is equal to one of the natural frequencies. So we note that because there is no damping, in the system, the FRF will be infinite when omega is equal to omega sub n, where n here is equal to 1 or 2. So one of the two natural frequencies for the system. And this is what we found when we looked at this example in chapter 3. We found that the FRF blew up at the natural frequencies. All right, we're going to take a look now at multiple inputs, multiple outputs, or MIMO systems, which is kind of just the general case of what could happen. So we're going to note that the FRFs are a representation of the system dynamics itself. They capture the dynamics of the system. So if you know the FRF of the system, you have effectively found the dynamics for that system. For single degree of freedom systems, the transfer function and the FRF are always a single equation. Regardless of how complicated the input is, you could have many different inputs. The input could be a compound function, but that doesn't matter. The transfer function will always be the same. So this is a case of what we would call a single input, a single output system, or a seesaw system. And generally for a single degree of freedom vibrating system, the output is the displacement of the oscillator. For MDUF vibrating systems, the transfer function and the FRF is an M by N matrix where M is the number of degrees of freedom and N is the number of inputs to the system. And if you generalize that from just an MDUF vibrating system to some multiple input, multiple output system or a MIMO system, then M is going to be the number of outputs of that system, and N is going to be the number of inputs to that system as well. With that being said, we're going to consider another example. We're actually going to look at two examples. The first will be for an MDOF vibrating system, and the second one is a system in state space form with with outputs as well. All right, so given here a system of two oscillators coupled together, we've included two grounding springs as well as dampers, both coupling damper and two grounding dampers. They all have different coefficients, and there are now two forces, one force acting on each of these oscillators. I've given you the equations of motion, and what you're going to do is you're going to compute the transfer function and the FRF matrices. First, you're going to do this using each equation separately, and then later on we'll do it with matrices. All right, so we're going to start by taking the Laplace transform of each equation. Take the Laplace transform of each equation of motion. This is going to give us Laplace transform of M1 x double dot plus Laplace transform of B1 plus B2 of x dot minus the Laplace transform of B2 y dot plus the Laplace transform of K1 plus K2 times x minus the Laplace transform of K2y. And then this is equal to our Laplace transform of F1 of t. Then for our second equation, we're going to get our Laplace transform of M2y double dot plus Laplace transform of B2 plus B3 times y dot minus Laplace transform of B2 x dot plus Laplace transform K2 plus K3 times y minus our Laplace transform of K2x is equal to the Laplace transform of F2 of t. It's going to give us two equations. First, we'll get M1 s squared plus quantity B1 plus B2 times s plus K1 plus K2 times x of s minus B2 times s plus K2 that times y. Y of s is equal to F1 of s minus or then the second equation is going to be minus b2s plus k2, all of that multiplied by big X of s, plus the quantity m2 times s squared, plus b2 plus b3, s plus k2 plus k3, that times big Y of s is equal to big F2 of s. All right, so we have two options now. First of all, there are going to be 4 transfer functions for this system. The first way we can solve that is to first set f2 to 0, and then solve these equations to obtain 2 of our transfer functions. We can then set f1 to 0 and solve the set of equations to find the other 2 transfer functions. Alternatively, we can put this into a matrix, and then we can compute the matrix inverse instead, and that's what we're going to do. So we're going to say, or, we're going to put this into a big matrix, where we'll have in here m1 s squared plus quantity b1 plus b2, that times s plus k1 plus k2. Down here, we're going to have minus the quantity b2s plus k2. Then I'm going to do the bottom right term first. This is going to be m2 s squared plus b2 plus b3, that times s, plus k2 plus k3, and then minus b2 s plus k2. This matrix times the vector x of s and then y of s. That is equal to f1, f1 of s, f2 of s. I'm going to call this big matrix here. We're going to say that this is, we'll just say this is q of s. This vector here we'll say is z of s, and then we'll just call the forcing f of s. Such that q of s times x of s is equal to f of s. Then, oops, that should be z of s. And z of s is going to be equal to the inverse of q of s times f of s. And then as a result of that, our transfer function g of s is going to be equal to the inverse of this matrix q of s. All right, so for a 2 by 2 matrix, let's say R is equal to A, B, C, D. The inverse of R is going to be equal to 1 over its determinant, which is A, D minus B, C, times the matrix D minus B minus C, A. Oh, I shouldn't have used Q up here. Hold on, let's change that to, we'll just use A. All right, so I'm changing that. I called this big matrix Q. I'm changing that to A because I used Q later on and didn't realize it. All right, and that's how we compute the inverse of this matrix. Q is the determinant of that matrix, and I've included it down here in the notes. So then we just need to fill in the other terms. We're going to get M2 S squared plus B2 plus B3 times S plus K2 plus K3. Over here, we're going to get B2S plus K2. Down over here, we're going to get B2 times S plus K2. And then lastly, we're going to get M1 S squared plus B1 plus B2 times S plus K1 plus K2. All right, so then we're going to plug in S equals J omega to find our frequency response function, and we'll get here K2 plus K3 minus M2 omega squared, that's our real component, plus J times the quantity B2 plus B3 times omega. Then we're going to get K2 plus J times B2 omega. We get K2 plus J B2 omega. And then this last term, we're going to get K1 plus K2 minus M1 omega squared plus J times B1 plus B2 times omega. And that is the complex frequency response function matrix. So there are 4 FRFs for this system, as shown here, which we will generally compute the magnitude and the phase, and then we'll plot those two. When we do Bode diagrams next, either on Wednesday or next week, that's what we'll see. Okay, we're not done just yet. So alternatively, we can convert to matrix form. This will give us our equation M1, 0, 0, M2 times X double dot and Y double dot plus B1 plus B2 minus B2 minus B2, B2 plus B3, that multiplied by X dot and Y dot, and then plus our Simpsons matrix K1 plus K2 minus K2 minus K2, K2 plus K3, times x and y is equal to our forcing vector f1 of t, f2 of t. Or we'll write this in our standard form, and mz double dot plus bz dot plus kz is equal to f of t. Once again, take a Laplace transform of this. In doing so, we're going to get that the quantity s squared times m plus sb plus k, all of that times big Z of s, is equal to big F of s. And then we can solve for Z of s. Z of s will be equal to the inverse of s squared m plus bs, or s times b plus k, inverse of that times f of s. And then the transfer function is g of s is equal to s squared m plus s times b plus k, the inverse of all of that. And the frequency response function, or FRF, is then simply h of omega is equal to k minus omega squared m plus j times omega b, all of that raised to the -1 as an inverse.